I wonder how many of you made any kind of a New Year's resolution? Couple of you. All right, so I don't want to put you on the spot and ask you what you resolved since it's just a couple of you, but all day long I've been hearing I'm going to eat healthier, I'm going to drink more water, I'm going to exercise more, I'm going to actually do my homework for a change. So it seems like we tend to make resolutions about our health, or we make resolutions about our schedule, or being more organized, or being more efficient, or something along those lines. I would encourage you to as well. I don't really make New Year's resolutions, but I do like to kind of stop at the end of one year and the beginning of a new year and just kind of evaluate my priorities. Like, it's really easy for me to get so busy doing the urgent stuff that I forget about the really important stuff. Like, my life just gets so chaotic and I get so busy going through my checklist and my to-do list that the things that really matter most sometimes get pushed by the side. And so it's good for me to just kind of reevaluate and reprioritize. So I would encourage you to maybe think about making some spiritual resolutions this year, or setting some spiritual priorities, maybe, if you want to think of it that way. If you're not in the habit of having a quiet time each day, that might be something that would be a great thing to start. Like, you could grab an online devotion, or you could even pick up, if you'd rather, pick up like a devotional book or something for your Kindle that would just be like a quick little 5-minute thing specifically for students that would be relevant for you. If you'd rather read something from the Bible, a really great place to start is in the book of Proverbs. There are 31 books in Proverbs and 31 days, 28 to 31 days in the month. So it's really easy. You just pick up and you read the proverb for that day in the month. Proverbs are all about wisdom, and a lot of you are making some important decisions right now and could really use some clarity for direction for the future, and so that might be something interesting to you. Psalms are another really great thing to read. A lot of people like to read a psalm and a proverb each day because Proverbs are heavy and all about wisdom and contemplation, and Psalms are usually lighter. They're like songs and they're encouraging. David wrote a lot of the Psalms when he was going through crazy, distressful times. So when you're stressed out and you're reading through and you're reading this psalm about how David is so overwhelmed and he's got so much on him, a lot of times you can relate to that. And then he'll talk about how God is his rock and his fortress and his strength and is going to see him through that. Now, David most of the time was being pursued by somebody who wanted to kill him. So it's also really good for me to go, my life is not so bad. This is not what I'm having to deal with that I'm so stressed out about. If you're more of a New Testament kind of person, or you might prefer reading that, then you might want to start with one of the Gospels. I love Luke, mainly just because it was written by a doctor. It's really down to earth in terms of looking at the human side of Christ. It talks about he was hungry and he was tired and he cried and he, so you can really see his humanity. A lot of people like the Gospel of John as well. So just an encouragement to you that if you're not in the habit of doing that, maybe just start your day, or if you're a night person, end your day with just 5 minutes and try it and see if that makes any kind of a difference for you. Mark 12:30 is one of my favorite verses, and it says, love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. And I think a lot of times we kind of brush over that with all your mind part. Like, okay, I have to love him with all my heart and with all my soul and with everything that I have within me, all my strength that I can muster. But the cool part about that, when you love the Lord with all your mind, God gave you your intellect. So when you are working hard and studying and doing your best as a student, that's a way that you can show God that you love him. That's a way that you can honor him. That's a way that you can please him. So it's great because you get to be a good student and please God at the same time. 2 Timothy 2:15 says, study to show yourself approved unto God. So again, you can honor God and show him your love just by being a good student. So just some encouragement to you as you start this new quarter, new semester, new calendar year, and for us working on this more challenging content in trigonometry. Okay, so when we left off at Christmas break, we went ahead and we got just a brief introduction to trigonometry in section 4.1. So back in section 4.1, they told us that trigonometry means the measurement of triangles. So initially, trigonometry dealt with the relationships among the sides and the angles of the triangles, and was used in the development of astronomy, navigation, surveying, and then we went on to calculus and physical sciences, and I mean just unlimited applications of trigonometry. We also looked in 4.1 at the degrees and radians and how we could convert back and forth between those, and we've talked about how as we move through this third quarter, we're going to get to the point we work much more in radians than we do in degrees. So in sections 4.2 and 4.3, they introduce us to the 6 trig functions that we're going to work with nonstop throughout our study of trigonometry. We're actually skipping section 4.2 today and going to section 4.3, and then we will come back to section 4.2. The reason for that is, if you'll notice there on page 295, section 4.2, it says there are 2 historical perspectives of trigonometry that incorporate 2 different methods for introducing the trig functions. Our first introduction in our textbook in section 4.2 to these functions is based on the unit circle. This is a unit circle. You may have never seen that before in your life. So if you look over at section 4.3 on page 303, it says our second look at the introduction of trig functions is from a right triangle perspective. Oh, right triangles. We're much more familiar with those, right? So if I have 2 different ways of introducing a concept to you, one of them you are extremely comfortable and familiar with, and one you've never seen before in your life, yeah, I'm definitely going with the triangles first, and then we'll go back to the unit circle tomorrow, okay? So we are going to start with 4.3 today with the introduction for our 6 trig functions. All right. When we are working with a right triangle, there's some terminology that they're going to use that we want to be familiar with. When we're working with our right triangle, the side opposite the right angle, so if you take your right angle and you go straight across from it, the side opposite of that right angle is always going to be your hypotenuse, and it's going to be the longest side of the triangle. Additionally, they're going to indicate for us one of the acute angles of the triangle to work with, and directly opposite that acute angle, we'll call that the opposite side. The third side we'll call the adjacent side. Now, honestly, this side is adjacent to the angle and the hypotenuse is adjacent to the angle, but since we've already got the hypotenuse labeled, it'll be easy for us to see which one they want us to label as the adjacent side. With our 6 trig functions, they can only be used in 2 situations. They can only be used when we're working with a right triangle. So they don't work if it's not a right triangle. And on that right triangle, they can only be used on the acute angles, not on the right angle. In a right triangle, both of the other 2 angles that you have are always going to be acute angles, right? If you think about it, 180 degrees in the triangle, 90 degrees in the right angle, that means the other 2 have to add up to be 90. So they're both going to be acute, right? Less than 90 degrees. So as long as it's a right triangle and I'm not working with the right angle, then I'll be able to use those 6 functions. Okay, so what are the 6 trig functions that they want to introduce us to today? Well, they're there on page 303. Right triangle definitions of the trig functions. They tell me that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and then cosecant is hypotenuse over opposite, secant hypotenuse over adjacent, and cotangent adjacent over opposite. You'll notice that cosecant is the reciprocal of sine. Like literally, all I have to do is flip opposite over hypotenuse to get hypotenuse over opposite, right? And similarly, secant is the reciprocal of cosine, And cotangent is the reciprocal of tangent. So most of the time, they're going to ask me to find the 6 values for those 6 functions. So here's the first big trick that we want to take advantage of. If I will be careful to write the reciprocals side by side, I always want to make sure that I write sine beside cosecant, cosine beside secant, and tangent beside cotangent. Then what I can do is find these first 3 values and then just flip them to get these next 3 values. I'll show you that in just a second. So every time I write the 6 trig functions, you're going to notice I always write those reciprocals directly beside each other so that I can take advantage of that. For some reason, people don't have any trouble remembering that tangent and cotangent are reciprocals of each other, but they get these other ones confused all the time. Like they can't remember with sine, am I supposed to put cosecant with it or secant with it? I can't remember. So here's an easy way to remember that. In those reciprocals, each pair, there's one that starts with an S and one that starts with a C. So like you can see one that starts with an S, one that starts with a C. Over here, one that starts with a C, one that starts with an S. So if you accidentally put the sine and the secant together, you would know, oh, hang on, I did something wrong because I've got 2 S's, or if I put the 2 C's together. So that'll be an easy way to keep that straight. So that means that really, instead of having to memorize 6 of them, I could just memorize these 3, and then I could flip them to get these other 3, right? Because our goal here is we're going to have a ton of memorization to do for these first couple of weeks. So we want to try and minimize it any way that we can. I also am terrible at memorizing things. So I have to have some type of a mnemonic device to help me remember anything. So I'll always try to give you some type of a tool that you can use to help you remember it as well. So when you learned those definitions the very first time, may have been in a geometry class, or it may have been in like your conceptual physics class or something like that. There may have been some type of a mnemonic device that you used. We'll provide one here as well, but whatever works for you, you have to know these 8 formulas tonight. Now, when I say memorize tonight, I mean memorize tonight, because tomorrow we're going to come in and we're going to have maybe 10 new formulas. And the next day we're going to come in and we're going to have like 10 new formulas. You can't wait until the night before the quiz or the test and try and cram all of that into your brain. It's not going to work. I don't know how to tell you any more clearly than this. You will fail every single test and quiz until you memorize this stuff. Because it's going to be on every single test and quiz all quarter long. And for the first 2 weeks, we primarily memorize it. And then for the whole rest of the quarter, we have to apply it. So if you don't know the formula, you surely then can't apply it to something else, right? Okay? So again, we're going to try and break this down into digestible amounts each day. But when we say memorize this tonight, you have got to stay on top of that. Make yourself flashcards, whatever you need to do, but stay on top of it on a daily basis. Okay? So, mnemonic device for these guys. Maybe you learned Chief SOHCAHTOA, right? Chief SOHCAHTOA was sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. My problem is I stink at spelling, so if you can't spell SOHCAHTOA, it doesn't do you a whole lot of good. So my conceptual physics teacher did a word association, and so that's how I remember them. That might be another option for you, where we said, okay, since sophomore and sine both start with S, I'll associate sophomore with sine. And so it will be sine is opposite over hypotenuse. And then cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we did a word association. So again, whatever works for you, whatever way you learned it, you've got to know those 6 definitions. Okay? Now, you'll notice that tangent and cotangent have additional definitions. Tangent is not only opposite over adjacent, but it's also sine over cosine. How in the world can it be 2 different things at the same time? Well, if we go through and we say, okay, tangent is sine over cosine. Sine, we defined as opposite over hypotenuse. And cosine we defined as adjacent over hypotenuse. So that's sine divided by cosine. When you divide fractions, remember that dividing is multiplying by the reciprocal. Keep, change, flip, right? So the hypotenuse would cancel out, and I would be left with opposite over adjacent. So you just proved for yourself that sine over cosine really is the same thing as opposite over adjacent, so it can have those two different definitions. And of course, once you know the definition for tangent, then you can just flip it because cotangent is reciprocal. So in essence, we need to learn 4 definitions, and then we can flip those to get our other 4. But we need to know those 8 tonight. All right. Once we learn them, what are we going to do with them? Look at example number 1. Example number 1, they give me a figure, and they have labeled the 2 legs, but they haven't given me the hypotenuse. So how can I find that? It is a special triangle. If it were not a special triangle, how can I find it? Pythagorean theorem, right. Because it is a special triangle, anybody know what that value is? 5, yes. It would be in our best interest to recognize that 3, 4, 5 triangle when we see it, because we're going to see it a lot. And it would be nice to not have to do the Pythagorean theorem every time we see it. The reason we see that one so often is, how often is it that you do Pythagorean theorem and you get a nice, pretty, clean, neat whole number, right? Most of the time you get a decimal or a radical or a something else. So there are a couple of those triangles, 3, 4, 5, there are a couple of them, 5, 12, 13, that they'll show up more often than others. Not saying that we won't have to work with decimals and radicals. We will, but we want to try and recognize those when we can. Do watch out, though, because if your one leg is 3 and your hypotenuse is 4, your other leg is not 5, right? The hypotenuse has to be the longest side. All right, so now that we've got all of the values, let's label them. They've identified this as the acute angle that they want us to work with. So what is opposite of that acute angle, the 3, 4, or 5? The 4. What's your hypotenuse? 5, because it is opposite the right angle. So by process of elimination, then that means our adjacent side is going to be that 3, right? Once I have them labeled, I'm literally just using direct substitution. I'm just plugging numbers into formulas. We said that sine was opposite over hypotenuse. So I can come over here and say what was opposite? 4. And what was hypotenuse? 5. So I can say 4 over 5, and that's going to be my sine value. We said that cosine was adjacent over hypotenuse. So what's adjacent? And what's hypotenuse? So cosine would be 3/5. We said tangent was opposite over adjacent. What's opposite? What's adjacent? So we'll get 4/3. We said cosecant was hypotenuse over opposite. What's hypotenuse? What's opposite? So we'll get 5/4. And you'll notice that that would have been the same thing as if we had just taken the 4/5 and flipped it, because they're reciprocals, right? So you can continue to use the definitions all the way down here, and you'll come up with the right answers, but you also can just take your value over here and use the reciprocal to come up with that answer as well. So as long as I write them in those reciprocal pairs, I can use the formulas to find the first 3 and then flip to find my second 3. All right? When you were in geometry, there were 2 triangles that you lived off of, right? A 45-45-90 and a 30-60-90. All right, the 45-45-90 is a special case triangle. What kind of triangle is it? Two sides are equal, or two angles are equal. Isosceles, yes, an isosceles right triangle. If you have a 45-45-90 triangle, it's going to be an isosceles right triangle. So because 2 of your angles are the same, then that means that the 2 sides opposite them are going to be the same as well. So let's say that they were 1, okay? If this side is 1, then this side also has to be 1 because they're isosceles. Pythagorean theorem to find the other side would give us square root of 2. The cool thing about the isosceles right triangle is that it always maintains that relationship between the sides. Like you can go through and multiply every one of these by 5 and it will maintain that same relationship. So you would have like 5, 5, 5 square roots of 2, or 10, 10, 10 square roots of 2, or 100, 100, 100 square roots of 2, whatever you want to do. All right, so they asked me to take the 45, 45, 90 triangle and to find the 6 trig functions for the 45-degree angle. Which 45-degree angle? It does not matter. Because if I look at this 45-degree angle right here, what is opposite of that angle? 1. If I look at this 45-degree angle right here, what is opposite of that angle? 1. So it's not going to make any difference. Opposite is going to be 1. What's your hypotenuse? Square root of 2. It doesn't matter which angle I'm looking at. And so by process of elimination, then the adjacent side would also be 1. So again, it wouldn't matter which of those I looked at. So now that I've labeled the opposite and the adjacent and the hypotenuse, then I can go through and fill in. All right? So what is our definition of sine? If we say it 573 times before our next test, maybe we'll remember it, right? So what's our definition of sine? Opposite over hypotenuse. So if I put opposite 1 over hypotenuse square root of 2, then I'll have my sine value. We are never going to leave a radical in the denominator, so we're going to need to rationalize that. So let's multiply top and bottom by the square root of 2, and we'll have square root of 2 over the square root of 4, so square root of 2 over 2. All right, what's your definition of cosine? Definition of cosine. Adjacent over hypotenuse, right. So if we put adjacent over hypotenuse, what are we going to get? Same thing. 1 over the square root of 2, which rationalizes to be square root of 2 over 2. What's your definition for tangent? Opposite over adjacent. So if I put opposite over adjacent, I get 1 over 1, which will give us 1. All right, definition for cosecant. Hypotenuse over opposite. So I could put the hypotenuse of the square root of 2 over the opposite of 1, or I could flip the answer that I had over here. Now, if I'm going to do that reciprocal thing where I'm going to flip it, don't flip the rationalized answer, because then you're going to have to rationalize again, right? Go back to what you had before you rationalized 1 over the square root of 2 and flip that, and flip that one to get square root of 2 over 1. If you flip this one, you're still going to get the same answer, but you're going to have to rationalize again, and then you're going to have to reduce and just do extra work you don't want to have to do. All right, so how about secant? What's our definition of secant? Hypotenuse over adjacent, and what are we going to get? Square root of 2. What's our definition for cotangent? And what are we going to get? Perfect. Now, we will get to the point that they tell us that we have to memorize those 6 values for the 6 trig functions of a 45-degree angle. You absolutely could do that, and by the time we get there, we will have used those enough that you might have them memorized already. But you could see, you could very easily generate them without having to memorize them when we get to the point that we just have so much stuff we have to memorize. All right, let's look at the 30, 60, 90 triangle. That is the other triangle that you use non-stop in geometry and that we are going to use non-stop in trigonometry. In a 30, 60, 90 triangle, there is also a special relationship between the sides. When you were in geometry, you were probably taught that if your hypotenuse was 1, then the side opposite the 30-degree angle would be 1/2 of that value, and the side opposite the 60-degree angle would be square root of 3 over 2 of that value. You definitely can go with that, but what our textbook has done is if you want to get rid of fractions, you multiply by the least common denominator, right? So to get rid of those fractions, they just went through and multiplied everything by 2. So if you multiply everything by 2, then you can say, okay, whatever your hypotenuse is, in this case it's 2, what's opposite the 30-degree angle is going to be half of that, and what's opposite the 60-degree angle is going to be square root of 3 over 2 times that. So in that case, that gives us the ratios of 2, 1, square root of 3, and I don't have to deal with those fractions, even though the ratios are the same. And again, that same relationship is maintained if I go through and multiply by a quantity. So like if I multiply everything by 5, then I've got 5, 10, 5 square roots of 3, or 10, 20, 10 square roots of 3. It's going to maintain that same relationship. All right, so if I am asked to find the 6 trig functions for the 60-degree angle, let's start with that one. For the 60-degree angle, if I'm looking at the 60-degree angle, what is opposite of that? What's opposite my 60-degree angle? Square root of 3. What's my hypotenuse? Because it's going to be opposite that right angle, and so by process of elimination, 1 is going to be my adjacent side. So opposite is square root of 3, adjacent is 1, and hypotenuse is 2. So go ahead and use your definitions to fill in your sine, cosine, and tangent values. All right, what'd you get for sine? Square root of 3 over 2. All right, what'd you get for cosine? Everybody, 1/2. What'd you get for tangent? Square root of 3. So a square root of 3 over 1, and we'll simplify it to square root of 3. All right, then we can come over here and use our reciprocals. So what would the cosecant of 60 be before we rationalize it? 2 over the square root of 3. And then if we rationalize that, multiply top and bottom by the square root of 3. So we'll have 2 square roots of 3 over the square root of 9, or 2 square roots of 3 over 3. All right, what about the reciprocal of 1/2? And then what about the reciprocal of the square root of 3 over 1? Yeah, I'll have 1 over the square root of 3, and then I'll need to rationalize that to get square root of 3 over 3. All right, then they asked me to give the 6 trig functions for the 30-degree angle. So I'm going to go back to that same triangle, but this time I'm going to look at the 30-degree angle. So if I'm looking at this 30-degree angle right here, what is opposite of that 30-degree angle? 1. Well, hang on. I thought you said opposite was square root of 3. We did when we were working with the 60-degree angle. If you're looking at the 60-degree angle, yes, what is opposite of that is the square root of 3. But if you're looking at the 30-degree angle, what is opposite of that is 1. So you have to look at the specific angle of the triangle they ask you for. All right? So opposite of that 30-degree angle is 1. Does the hypotenuse change? No. So the hypotenuse is still going to be 2. And so then for my adjacent side, even though both of these are adjacent to 30, since this is my hypotenuse, then square root of 3 will be my adjacent side. And again, I could get that by process of elimination. All right? So now that we've defined the opposite, adjacent, and hypotenuse, go ahead and fill in your sine, cosine, and tangent using your formulas. All right, what'd you get for sine? Yeah, 1/2 or 1 over 2. What'd you get for cosine? Square root of 3 over 2. And what'd you get for tangent? I got 1 over the square root of 3, which again, when I rationalize, is square root of 3 over 3. Didn't I do that same rationalization a second ago? Oh, it's kind of strange. All right, so then we'll take the reciprocals. So if we flip 1/2, we get 2. If we flip square root of 3 over 2, we get 2 over the square root of 3, and I got to rationalize that. Oh, it's like deja vu. I swear I just did that same thing a second ago. I did. Right there. And I did this one. Right there. And if I keep going with the cotangent, I did that one. Right there. Is that just coincidence? No. There's the theorem that says the cofunctions of complementary angles are equal to each other. Okay, one piece at a time. I don't have a clue what you just said. All right, let's talk about this first piece right here, cofunctions. What are cofunctions? Cofunctions are sine and cosine. If you take sine and you put co with it, you get its cofunction. If you take cosine and you take co away from it, you get its cofunction. So what would the cofunction be for secant? Cosecant. What would the cofunction be for cotangent? Tangent, right. So these are the cofunctions, sine and cosine, tangent and cotangent, secant and cosecant. They are not the same thing as the reciprocals, right? When we do the reciprocals, like I can take cosine and turn it upside down to get secant, that's not the same thing as what I have down here. It's different, so keep that straight. Reciprocals, cofunctions, not the same thing. All right, so cofunctions of complementary angles. What are complementary angles? Two angles that add to be 90 degrees. If you are working with a right triangle, both of your acute angles are always going to be complementary, right? Think about that a second. If you're working with a right triangle, your acute angles of that triangle are always going to be complementary, right? So this is going to show up a lot, right? It's not some obscure kind of thing. So cofunctions of complementary angles are equal to each other. That's why the sine at 60 was the same thing as the cosine at 30, because sine and cosine are cofunctions and 60 and 30 are complementary. So if you're working with a right triangle where your acute angles are always complementary of each other, then you could go through and say the sine here is going to be the same as the cosine here. The sine here is going to be the same as the cosine here. The tangent here is going to be the same as the cotangent here. The tangent here is going to be the same as the cotangent here. The secant here is going to be the same as the cosecant here. And the secant here is going to be the same as the cosecant here. That will always be the case. Okay, how do I write that as a formula? Well, they've come down here and they've written it 6 different ways, and we've said memorize this tonight. Honestly, if you understand the reasoning behind this, you don't have to memorize a formula, right? Because all that we're doing is just going through and writing the cofunctions, sine and cosine, cosine and sine. Those are cofunctions. Tangent and cotangent, cotangent and tangent. Those are cofunctions. Secant and cosecant, cosecant and secant. We're just writing the cofunctions in both orders, forwards and backwards, right? Then we're going through and saying, okay, if theta is 30, how would you find its complement? 90 minus 30. So all we're doing over here is saying to find the complement, just do 90 minus whatever your angle is. So this is just the angle and its complement, and we repeat that all the way down because we're saying cofunctions of complementary angles are equal to each other, right? So you can memorize those 6 formulas if you want to, or you can understand the process behind them, and then we don't have to memorize them.